Hello, okay. Assalamualaikum warahmatullahi wabarakatuh. So now is our second day. So we will start our slide for today. Okay, so for today we have we have two topics, which is one understanding rainfall for flood modeling, and two beyond hazard map, which is about risk map. And I've mentioned before about frequency analysis. So today there will be more on that about frequency analysis. And we are supposed to finish some quiz 2 pre-test by this morning, just now. And you estimated time for you to finish this video is at 2 p.m. And you can do your assignment and we will present at 3:30 p.m. Okay, first, before anything, or before we do hazard map, before we do risk map, before we do modeling, there is one important thing that we need to understand, and that is design rainfall. Okay, so the first step is to estimate design rainfall, and then we can do flood modeling. So flood modeling, just like yesterday, somebody presented on hydrological and hydraulic modeling. So this consists of for flood modeling, hydrology and hydraulic modeling. And then from there we can get some inundation areas, and then hazard maps, and then followed by risk map. So design rainfall, so this is what I mean that we are talking about frequency analysis. Okay, and then hydrological and hydraulic modeling. Okay, it's all about catchment and uh, the open channel, the river, and finally hazard map or risk map. Okay, so this is a typical of an IDF curve. So it's an intensity, duration, frequency curve. So if you're from GPS, from Department of Irrigation and Drainage, I'm sure you are very familiar with this. And anybody from consultancy, if they have done some design, rainfall design, so this would be familiar. So what we have is we have the duration, we have the rainfall intensity, and then we have the return period. So that is why it's called intensity, duration, and frequency curve. Okay, so this is actually the how we get the design rainfall. Okay, so from design rainfall we do flood modeling, and then we can get some kind of a hazard map. And beside hazard map, what we can do with that is we can classify some vulnerability, where are the areas which are vulnerable, and then we can get some kind of like a risk map. Okay, so we come back to this IDF curve because this is the most important. Okay, how do we get this IDF curve actually? So this IDF curve is developed by frequency analysis. Okay, so frequency analysis, it relates to the return period. Okay, it's a probability. It relates to probability, and probability relates to a return period. So how do we do frequency analysis? So the most basic data is we need to have some a series of data. So for example, if we are doing on flood, on extreme rainfall, so we have if we want to do a frequency analysis using extreme rainfall series, so for example, the most frequently used is using annual maximum data. Okay, for this example, let's say we use a daily rainfall, so we need to have a time series of an annual maximum daily rainfall. So this is the basic data, for example. Okay, so this shows maybe we have 3 stations. So if we okay, so this is actually what data. Okay, data collected. Okay, so each year we have a data. So when we have a collections or a series of data, so we can call it a annual maximum series or annual maximum daily rainfall. So for this case, it is a daily rainfall. Okay, so then we have using this data, we can develop this PDF probability density function. So what is this? So the y-axis, this is probability. Okay, and then the x-axis, so this is the data. Okay, the annual maximum data. Okay, so what does this mean? It means that for this case, a 50 millimeter rainfall, okay, for example, in the range of 10, 20, 30, 40 to 60, okay, the data in the range of 40 to 60 millimeter will have a probability of about 0.002. Okay, this is what it means. Okay, so for example, we have a data between 60 to 80 millimeter rainfall, so the probability would be okay, around what 0.01 probability. Okay, so this is PDF. So from the annual maximum series, we need to convert it and make it into a like a probability graph. Okay, so this is where you know that we have like a normal Gumbel. There are a lot of distribution models. So these are distribution models. So we need to fit our data. For example, our data is this histogram. So we need to fit which distribution model fits our data. So this is one of the steps for frequency analysis. Okay, so I hope you understand what PDF is. Okay, so PDF again, the y-axis is the probability. Okay, so if we say it is a model, so it means it is a continuous line. Okay, so if the slide before it uses like a histogram, right? The histogram may look like this. So if it's a histogram, it's discrete. Okay, it's not continuous, meaning that if you have a rainfall, the histogram is just a range of rainfall data. Like the probability is for a range of rainfall data from 40 to 50 millimeter rainfall, and then we have the probability. But if we know the distribution model, okay, we know the distribution model. Okay, so distribution model is a model. Okay, it's a mathematical model, mathematical equation. So it is continuous. Okay, so any rainfall data, any 50.1, okay, 51, 50.2, 50.3, so all rainfall data will have its own probability. So that is why it's important to convert it into a distribution model. Okay, one thing that it can I mean interpolate or extrapolate, you can say that the data that we don't have, so we may know its probability. Okay, because data that we have is only observed data. Okay, the data is a lot actually. It's not just what we observe. So if we make it into a distribution model, then we can fit any rainfall data. Okay, so any rainfall data will can have its probability. Okay, the other one is this. This is also important. Cumulative distribution function. Okay, so cumulative means it just adds up the PDF. Okay, it's a cumulative of the PDF. So cumulative distribution function. Okay, it's the cumulative of this PDF. So that's why if we that's why for CDF the highest value is 1. Okay, but for PDF, okay, if we add all this data, okay, we add all this probability, okay, according to each data, so we can get 1. Okay, so that is why if we add the PDF, we will get 1. And then for cumulative distribution function, the highest value is 1. Okay, so it's a cumulative of the PDF. Okay, so this is important here. Okay, because this is where Okay, this cumulative distribution, cumulative probability. So this is where we get our return period, or for Malaysia we use ARI. Okay, so from this we get the return period. Okay, so we have our data, the annual maximum series data, and then we not convert, we analyze it, and then we fit to the best distribution model. So then we can get the PDF, okay, according to what distribution model. So each distribution model, it has some formula. Okay, there are some equations. Okay, so we have PDF, and then we convert it into a cumulative distribution function, a CDF, and then from that value we can get our return period. Okay, so this is how the IDF curve is calculated. Okay, so uh, for each return period, so what is the rainfall value? Okay, so how do we fit which distribution models? Okay, which distribution model fits our data? So there are tests, and we can do some tests. Okay, this is just for information. So for example here, like standard least square criterion, correlation coefficient, maximum not likelihood. So these are all a goodness of fit tests. Okay, so the best fit distribution is used to estimate the return periods and quantiles of the extreme values. So in this case, if we are working with rainfall data, so extreme values means the annual maximum series. Okay, the rainfall data, and then quantiles means the values of that rainfall data. Okay, for example, like for 100-year return period, so what is the rainfall intensity? Okay, so the rainfall intensity here is the extreme values, or the quantiles. Okay, so we have a lot of distribution models. Okay, but here it says as distribution functions, so it's the same, distribution functions and distribution models. So I think most of you know about normal, okay, Gumbel. Okay, but actually for extreme values, if you are dealing with like you are dealing with designing, okay, for flood or any hydraulic structures, so it's supposed to be extreme. Okay, it's extreme values. So there is some basic distribution models or distribution functions which are suitable for extreme values. For example, here log normal, generalized extreme value, in this case GEV. I've mentioned GEV in the previous in yesterday. And then log Pearson. Okay, so why is this why is this distribution functions are chosen for extreme values? Okay, it's because if you see the tail of this distribution, if it's normal, okay, this is normal. So normal, okay, so here is probability, and here is the x-axis is the rainfall data. So if you use normal, so this means that the minimum, okay, values and the maximum values, uh, it it has the same uh, difference, okay, between the mean. Okay, so what is mean? What is average? So average is actually here. This is average. Okay, the highest probability is average data. Usually, this is what average means. It means that mostly the average value has the highest probability to occur. Okay, but for extreme values, sometimes it's not a normal distribution. Okay, it should have like this kind of distribution. Okay, oops, belajar. Okay, so let's say again, y is the probability, and then x is the, okay, x-axis is the rainfall data. So if it's an extreme value, so it should have like a tail skewed to the right. Okay, this is what we mean by a tail skewed to the right. to the right, means that there are high values here. Okay, and then it's far from the average. Okay, the highest rainfall data, okay, is very far from the average. So that is what we say distribution functions which is suitable for extreme values. So another example is we can say that this kind of distribution model is suitable for Kelantan. Yeah? For example, Kelantan have extreme data which is very far from the normal. Okay, what I mean by extreme data is, for example, it has this kind of, let's say this is 500. Okay, let's say this is 500. So it's very far from the average value. Okay, but if it's, let's say in Kuala Lumpur, the rainfall data in Kuala Lumpur, so usually it might be a normal distribution where the maximum and the minimum has um, I mean has the difference between the average is not so far. Okay, so this is why different location may have different distribution model or distribution functions. Okay, so for each distribution function or distribution model, it has some parameter. Okay, you may relate this to, if you know this, you should know this one. Y equals to mx plus c, right? Okay, so this is a model. This is also called a model. So this is a model for a straight line. Okay, so the parameter is, what is the parameter? The parameter is m and c. Okay, so for distribution functions, it's the same thing. Okay, but for distribution functions, the shape is like this, right? It's like this curve, or this curve, or this curve. So all of these are distribution functions or distribution model, where the y-axis is probability, okay, and the x-axis is any data, but for this class it will be rainfall data. So also like a straight line, have a parameter of m and c, okay, but c is constant. Okay, m may change. Okay, it depends on the data. So this is the same as well for a distribution function or a distribution model. So it has its parameter. Okay, but the parameter is location parameter, scale, skewness, kurtosis. Okay, so for location parameter, what is location parameter? Okay, so location parameter is where is the center of the distribution model. For example, this red one is, okay, so the location here. So the location is actually the average or the mean. Okay, so this, the location parameter, so this red distribution is here. Okay, and it can be here. So for the next, for this second distribution model, so the location parameter is here. So that is what location parameter means. Okay, but for scale parameter, oops, for scale parameter, so scale is more like how far. Okay, you can look at this red and green. Red and green. You can look at red and green. So red and green. So scale parameter is how far the minimum, okay, so minimum here and the maximum here is far from the average. This is average. So again, and for the green line, this is more further. Okay, so this is the scale parameter. How far the minimum and maximum data is from the average. Okay, and what else we have here is skewness. So skewness is actually this orange orange, we can see it's skewed to the right. Okay, it can be skewed to the right, or it can be skewed to the left. Ni dah. Okay, so this means skewness. Okay, so it also means some things. For extreme data, extreme values, if we're dealing with extreme values, it should be skewed to the, it should be skewed to the left, okay? Because extreme data, let's say this is X, this is probability, okay, X is rainfall data. So skewed to the right means the high, the maximum values, okay, is very far from the mean or the average. Okay, this is X bar. I use X bar as minimum or average. Okay, so that what skewness means. Okay, and last is kurtosis. So kurtosis is, you can look at this one, red, this red, okay, and this green line. Okay, so this is kurtosis. How far the probability goes up. Okay, so that is kurtosis. So these are all distribution model parameters. So remember yesterday I talked about stationary and non-stationary. So before climate change, we assume all these parameter is stationary. Okay, it will be the same for tens of years. But now, because of climate change, this parameter might change according to time. Let's say this 10-year in Kuala Lumpur, the distribution parameters is like this, and then the next 10 year these parameters might change. So that is what we say a non-stationary parameter. Okay, so this is a repeat. For example, location parameter or mean. I'm sorry, not minimum but mean. It means average. Okay, so it can move right or left. It means that, let's say, for a rainfall station in Kelantan would have the location parameter more higher, okay, because it has a higher distribution of rainfall values. Before it was here, so if like but this is negative, let's say not there, but wait, let's say the other one is here. Okay, so the location parameter is about here. So this might be stations where its rainfall is not so high compared to this one. Okay, so this would be a distribution of rainfall from a station which has quite high rainfall data. Okay, so this is a scale parameter. So we can see that okay, difference macam ni, dia macam kangkang dia lah, ada kangkang dia. Okay, so this is more smaller, and the red one is larger, and the blue one is largest. So this is what we call scale parameter. How far the minimum and maximum. Okay, this, let's say for the green line, the minimum and maximum, how far it is from the average. Okay, so we can see that the blue distribution model is more far. Okay, the minimum and maximum is much far to the average. So this shows, for example, a rainfall station which has a lot of variable of rainfall data. It has dia punya perbezaan between minimum and maximum tu sangat besar. Julat dia besar. Okay, so that is scale parameter. Okay, and we have skewness. Dia skew, macam mana dia skew to the right. So if it's more skewed like this, yang biru ni, so it means okay, like this one, minimum dia jauh daripada average. So remember, average or mean, 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 okay, is the highest probability. Okay, so whether the distribution of rainfall data is skewed or not, it might be different between stations. Okay, and then last, kurtosis. Kurtosis, how how high the probability is, and um, dia punya perbezaan julat tak ada beza, but how high the probability is. Okay, so what are the consequence of if we did not choose the right distribution model for your data? So this might happen. Okay, some extreme data might not fit your model. Let's say this continuous straight line is your model, and this blue dots is your rainfall, your data. So if we choose the wrong distribution model, so we might not fit all the data, observed data into your model. So this will affect your return period estimation. So it's really important to fit the right distribution model to the right data. Okay, for example, in Kelantan might have a different distribution model. For example, it might have a GEV distribution model, but Kuala Lumpur might have a Gumbel or normal. So if you fit it not correctly, then you will underestimate, or you overestimate. Overestimate is still okay, but if you underestimate, what will happen? Let's say you estimate a 100-year rainfall for Kelantan is 500 millimeter, but because you use the wrong distribution model, so your results or your analysis shows that your 100-year return period rainfall is let's say 200 millimeter only. So that is very not good because you underestimate your design. Okay. Okay, so these are example of if we fit some data for a different type of distribution model. So here for this case, it's not that much different. Okay, let's say if you use GEV, then you will get the rainfall value for a 20-year return period as 334 millimeter. Okay, remember this is what we call quantiles. Okay, it's the value of the return period. Okay, so if you use Gumbel, it's 341. If you use normal tree, it's 326. So it will vary if you use different distribution model. Okay, and another point here is this is for less than 100-year return period. Okay, and for if we use a more larger return period here, okay, I use T as return period here. Okay, for Malaysia, usually we use ARI, average recurrence interval, but this example uses T. It's the same thing. Okay, if we use a larger return period, or we want to estimate larger values of return period, so then we will have some discrepancy here, different estimation for different distribution model. So remember, how do we know which distribution models are the best? So we need to do I've mentioned before the goodness of fit test. GOT, goodness of fit test. Okay, so that is how we choose which distribution model is the best. Okay, and there are other kind of tests. Okay, there's a lot of process actually, so this is just an introduction. You don't have to worry if you don't really understand, but as long as you know there is different distribution model and you need to fit the best distribution model, so that is really important. Okay, if we want to estimate our own return period values, if we don't use the IDF curve, we can estimate by our own. Okay, so the IDF curve is developed from this, from frequency analysis. Okay, so what else? If uh, you want to design more, okay, higher return period values, so it is an option also to use this PMP, probable maximum precipitation. Okay, PMP is usually used for designing dams or hazardous landfills or whatever. So we might also use PMP, probable maximum precipitation. Okay, so if you see in MASMA, okay, the Malaysian Stormwater Manual, so it shows the typical steps to develop IDF curve. So this is actually a frequency analysis. Okay, it's the same thing that I showed you before. We have to collect some data, get the annual maximum, and then of course you need to test the quality and consistency of the data, and then we have to fit the rainfall data to various frequency distribution models. So which one fits your data the best? Okay, and then select the most suitable model. Okay, uh, this is a frequency distribution model. Okay, model, and then we can calculate the amounts of rainfall for various durations and select various return period, and then you can get the IDF curve. Okay, so again from the IDF curve we get the design rainfall, and then you can proceed until you get the hazard map and risk map. Okay, now we can look into how we can estimate risk, not estimate, develop risk map. Okay, it's from hazard map. Okay, so for these slides, okay, I took from Professor Kaoru Takara. I'm not sure if he teach you this semester. Okay, he was my PhD supervisor. So I did my PhD with him on statistical hydrology. Okay, so so what is the terminology of risk? So it's a possibility or chance of meeting danger, suffering, loss, injury. Okay. Crisis, turning point in illness, for example, danger, chance of suffering, liability to suffer. So we are interested on risk. Okay, so for hazard is actually risk, but more like a danger. Okay, then it can be game at die. So there's a lot of terminology. Disaster, great or sudden misfortune, terrible accident. So threat, okay, catastrophe, accidents. So these are all the risk. Okay, and what important here is, for example, resilience, okay, and vulnerability. So this is what we always use for calculating risk. So what are hazard and disaster? So hazard is phenomena that causes disaster. Okay, for example, earthquake, tsunami, typhoon, flood, landslide. So all of these are hazard. Okay, we cannot prevent hazards, but sometimes we can control hazard. Okay, for example, flood control. And we can prevent disaster and reduce disaster risk. Okay, by taking some countermeasure. Okay, so there are a lot of formula of disaster risk actually. There are a lot of formula and we cannot say that which one is right, which one is wrong. Okay, the formula of risk is still developing. Okay, but for example, some of the common components for disaster risk are, for example, hazard, exposure, vulnerability, and countermeasure. Okay, so hazard, exposure, and vulnerability is like negative, okay, things, but countermeasure is like positive. Okay, it will reduce the risk, but if we have higher hazard, exposure, and vulnerability, it will increase the risk. Okay, so we can organize our data. Okay, so the data, the information that we put into our components of hazard, vulnerability, and capacity, okay, we can separate it into like a natural, or is it social, economic, institutional, and physical. Okay, so for example, natural is mostly hazard like rainfall data, landslide. Okay, social economy is like population, income, asset. Okay, and then institutional is like the governance. Okay, any legislation, is there any budget? Okay, is there any disaster risk management structure or early warning system? Okay, inside the state, for example. So that is institutional. And physical is like infrastructure. Okay, any land use, housing. So we can to make sure that all these variables are included, so we can separate it into this kind of class. Okay, so what are the data for hazard, what are the data for exposure and vulnerability, and what are the data for capacity? So for example, for hazard, how do we quantify it? We may quantify it through, like for flood, we may quantify it through the depth, okay, the maximum flood depth. And then for landslide, the number of landslide, or earthquake magnitude. So we can quantify the hazard value from this. And also, how do we quantify exposure or vulnerability? Is that we can use data like population, income, asset, infrastructure, okay, housing, age. So these are all the data that we can use. It's not limited. There are many ways. Okay, depends on your clarification of the data that you used. Okay, and capacity or countermeasures. It might be they have some disaster risk management governance. Okay, DRM means disaster risk management. Okay, so if you have some risk management governance, if you have some legislation related to disaster, if you have a budget, okay, then that can be considered as data for capacity or countermeasure. Okay, and then what you can do is you can make a score. Okay, for example, for age, the variables of using age data, so you can make a score 0 to 4, and if it's least vulnerable, like for example the age between 25 and 35 is very least vulnerable, so the score is 0 or 1 should be like that. Okay, and then less vulnerable and high vulnerable, very high vulnerable. So if you have a very vulnerable characteristic of like kids and old people, so you may put a high score for vulnerability. So this is how you quantify and make it into values. Okay, so we go back to the terms of like hazard. So this we might explain it this way, uh, about risk, hazard, exposure, and vulnerability. Okay, so we may explain the difference between the correlation or the what interrelation between hazard, exposure, vulnerable, and safer place. So if we have a hazard, so hazard is the red color. Okay, hazard is red color, and then we have exposure, people and property, this one, and then we have vulnerable place, and we also have safer place. Okay, so for air A, okay, so A, serious disaster damage is possible because people and properties are exposed. Okay, and it's in a vulnerable place, so A is the most serious. And then B, people and properties are affected. B, okay, this is B. People and properties are affected by hazard, but there is no damage because they are not located in vulnerable place. Okay, and then C, the hazard hits the vulnerable place. Okay, it hits the vulnerable place, but there is no damage, because there are no people and properties there. Okay, I hope you are clear with this. Okay, so see here, okay, there are hazard, and then it's in vulnerable place, but there are no exposure to people or property, so that's why it says there is no damage. Okay, and then D, okay, so here is D. Okay, so it's in hazard, okay, it's hazard, but it's in a safer place. Okay, it's in a safer place, this green. So there will be no damage, because there is no exposures, okay, and are in safer place. Okay, and then last, which is E. Okay, Risky is risky, okay, but no damage, because exposures in the vulnerable place are about to hit by hazard, okay, but it does not reach them. Okay, it's the vulnerable place. There are people and property that are exposed, but the hazard did not hit. Okay, did not hit in E. Okay, so it's risky but no damage. Okay, so another way to put this is, for example, what do we do? Okay, metrics of risk management. So what do we do when we have the information of the risk? Okay, So if the frequency, for example, frequency of hazard is low or high here. Okay, and then the severity can be high or low. Okay, so we can decide what to do. We can decide if it's high frequency but the severity is low, we can just reduce, try to reduce the impact. And if high frequency means a lot of hazard occur and it will be very severe, so we need to avoid, okay, avoid in this case maybe do some mitigation, okay, or just don't make a development in that place because there's a lot of hazard and the impact will be very severe, so better just avoid and don't do some development in that location, or don't live in that location. Okay, and then if the frequency is low and this but the severity is high, so we may transfer. This means transfer means like an insurance. Okay, there are low frequency of hazard and but the severity is high, so there is a possibility of, we call it a transfer the disaster, or we can say like we make a insurance. And if the severity is low and the frequency is low, so just retain, just don't do anything, is also all right. Okay, so here another information. So if it's this part, so we may make some risk financing. Okay, and if it's high frequency and this part, we may do some risk control. So there are some methods that we may do is like reduction. We reduce the risk when severity of injury is typically low and the frequency is high. Take steps to reduce the frequency. Okay, better safety rules, equipment, grounds maintenance. Okay, avoidance. Avoid the risk. Don't offer as the risks are too high. When the severity of injury is high, injuries occur frequently, simply do not offer these programs. Or for example, I told you, simply just don't develop that area. Okay, and then retention. When injuries occur infrequently and are not severe, when they do occur, these programs can be continued with little change. Okay, for example, you go on and make some development there. Okay, and then transfer. Injuries are severe but don't occur very often. We can rely on insurance. Okay, we transfer the risk using money. Everything's about money, so we can make insurance so that we transfer the risk. Okay, so these are things that we can ponder. For example, 50 millimeter rainfall. It can be less than a glass. It can be, it doesn't matter. It can be 50 millimeter. So this is datum. Okay. So what does 50 millimeter rainfall means? Okay, but if we say 50 millimeter rainfall in an hour, oh, we can say, oh my gosh, it's serious. Okay, so 50 millimeter is still the datum, but we put some more parameter here in an hour. Okay, so which we can recognize as an important issue. Okay, so again, 50 millimeter rainfall in an hour, or we can say, oh, it's serious, and then roads may be inundated. Okay, so again, 50 millimeter is a datum, but if we know that 50 millimeter rainfall in an hour, okay, is serious, so it's like more meaningful information. Okay, and we have a knowledge about urban water disasters. Okay, when we have knowledge, then it becomes a meaningful information. Okay, so when we have knowledge, and we know that it's a meaningful information, 50 millimeter rainfall in an hour. So what we can do, okay, in disaster management, there is some wisdom to avoid or prevent disasters. So again, if you have knowledge, okay, 50 millimeter in 1 hour, it's an urban water disaster. And then if 50 millimeter in 1 month, it can be a water shortage. Okay, and for example, here it shows in Japan, annual average precipitation in Japan, 1,700 millimeter. Okay. It is natural to have rainfall of 100 to 300 millimeter in 1 month. So it depends on the location. Okay, so the message is based on knowledge, you can quantify the risk. Okay, so if you know, you have the knowledge, you can quantify risk. Okay, so you know how to calculate disaster risk, and then you have the knowledge, and then so how do we reduce? How do we reduce disaster risk from scientific, technological, and social aspects? For example, we can reduce the risk by public investment, risk avoidance by city planning and land use change. Okay, risk transfer by insurance or compensation. And then we can do some regional disaster prevention plan or emergency response. Okay, so that's finished. Our slide has finished. So for assignment 2, what you need to do is try to identify risk components. Again, find a suitable paper on disaster risk. Find out what are the components that are used in the risk model, okay, and how they quantify each component. So just make a short presentation. Okay, yesterday's presentation was really good, really compact and very informational. So I hope we will make the same sharing session as yesterday. So good luck, and we will see at 3:30 p.m.